So one of the topics that's covered by your book in this chapter, and it could be covered in this chapter or elsewhere, but they chose to cover it here, was expanding the idea of work to include other forms. So you've got du equals del Q minus del W, and in terms of heat, we say that there's two types of energy. There's heat and there's non-heat, and non-heat is work. So our dq, that's expressed purely in terms of the entropy, T ds, which means work is going to be everything else. And so far we've just talked about pressure volume work, P dV, but really it's anything in which you have some force and some conjugate distance that's associated with it, right? You remember from your freshman or sophomore physics class that if you have some block and it has some force on it and it moves, I'll draw that better, moves here by some delta x, the work done is just force times the distance. Another way to think about this is you can think about it in terms of potential energy. You have something and you raise it by a certain distance. Well, you've increased the potential energy by potential energy times delta x, the dx. And in the case of what I call chemical work, which is the work to add or remove content from the system, our potential is called our chemical potential, and our, you want to think of it as displacement, is the change in the number of atoms. Let's call this I. That is the chemical potential. Of species I, and that has units of energy per atom, or energy per mole, and then this is the change in the number of atoms or mole. Which will give you the energy. And when we think about this in terms of when we think about this in terms of our potentials, our thermodynamic potentials, we can think about this as being an add-on to the differential. So we have some dg is equal to dg by dt, dt plus dg by dp, dp plus sum I equals 1 to n dg dni dni. And this is being done now at constant pressure and constant number of particles. I'm putting this in curly brackets to specify the set of the number of atoms of each species. So there's capital N species. This is being done at constant temperature and chemical number. And then each one of these is being performed at constant temperature, pressure, and I'm going to call it Nj. And I'm saying that J is not equal to I. So it's all of the chemical components except for the ith one. So for example, let's say we have a gas, and the gas is going to contain, say, krypton and helium. Well, then we could write dg is equal to dg by dt plus dg by dp plus mu kr dn kr plus mu, or it's not mu, sorry, let me, I'm writing this out as in differential form. dg by dn kr dg by dn he dn he, and this is being performed at constant pressure n kr n he. This is being done at constant temperature n kr n he. This is being done at constant temperature, pressure, and n he, but nkr is allowed to vary. And this is being done at constant temperature, pressure, and n ke, allowing the number of helium atoms to vary. And the important thing here to recognize is that any of the work terms that you have, you know, electric field and electric displacement or whatever, you can just add on to this. So now that we have an expression for the chemical potential, or sorry, for our thermodynamic potential, we can specify that for the particular system that we're working with and the forces that come to bear. You know, stress strain, for example, could be a part of your Gibbs free energy. For those of you that are that really enjoyed our lecture in class on Friday and are interested in the Legendre transform expression, if you go back and you start writing this out, I do want to point out one interesting point that you're going to be a little frustrated with looking at the signs. And from my understanding of this, the real issue here is dealing with the sign of pressure. But we can talk if you want to outside of class about that. So now in this case here, this differential is minus s. This differential is plus v. This differential is mu kr, and that is mu he. And these are our chemical potentials. So we've got an expression now for, or a demonstration of how you can expand work, and an expression for chemical work. So finally, I'd like to kind of talk about the consequences of all of our work looking at thermodynamic potentials. and all the math. And kind of in summary, the consequence is simply that the first derivative of our potentials, those give us back our thermodynamic variables. Right, so taking the derivative, so dg dt constant pressure is negative S, and dg dp at constant T gives us our volume, and that just comes from dg is equal to negative S dt plus P VdP, right? And that follows naturally. Something that you haven't seen yet, and which I think is possibly a more significant consequence, is that the second derivatives they give us material properties, or let's just call it properties. So for example, if I take the second derivative of the Gibbs free energy with respect to temperature, that's going to give me the first derivative with respect to temperature of negative S, right? Because that's just from here. The first derivative gives me negative S. So now I'm taking the derivative of negative S, and then because dH is equal to T ds plus V dP, there's a few steps in this one, but V dP dH by ds constant pressure is equal to T, and I should point out this is constant pressure because we're doing Gibbs, and because we can say ds by dt times 1, and we're going to write out 1 as dH by ds by dH, that equals 1. Well, if we write that out, then we can say this is dH by dt ds by dH, and these h's just cancel. And that is equal to the constant or isobaric heat capacity 1 over T, where this gives us that. And this expression comes about because we know Cp is equal to dH dt P. Coming back up here, this is negative, playing negative out in front, dH by dt 1 over t is equal to negative Cp over t. And this is from one of our Maxwell relations. So that gives us the second derivative of the Gibbs free energy equal to the heat capacity divided by, or the constant pressure heat capacity divided by minus 1 over the temperature. And that step's a little more complicated. There's some simpler relations. For example, we have other measurable quantities such as the isothermal compressibility. E-I-L-I-T-Y. Compressibility. And the isothermal compressibility is minus 1 over V derivative of volume with respect to pressure, constant temperature. And we have the coefficient of thermal expansion. Which is defined as 1 over V, and then it's the change in volume with change in temperature. Well, we can say now that taking the second derivative of Gibbs with respect to the pressure is equal to the derivative of the volume with respect to pressure, constant T, and because we have this, we can now say that is equal to the kappa T. Those two are related. Or we could write second derivative of Gibbs with respect to pressure and temperature is equal to the second derivative of the Gibbs with respect to temperature and pressure, right? The order doesn't matter. Well, then we can just as well write derivative of entropy with respect to pressure at constant temperature is equal to derivative of volume with respect to temperature at constant pressure. And using this relationship, we're going to have is equal to V alpha. So either of these are related to this. So the real consequence of this is that because we can measure the heat capacity at constant pressure, or the compressibility at constant temperature, or the thermal expansion at constant pressure, isobaric, because we can make those measurements, once we know these, we can integrate to determine the thermodynamic potentials. So we say ME measurement yields the thermodynamic potentials. And that's a big thing. I mean, there's no instrument that you can use to measure Gibbs free energy, but measuring these allow you to determine the Gibbs free energy. And whenever we get to the next chapter, chapter 6, we're going to be talking about the thermal properties, in particular with respect to heat capacity. Okay, let's solve problem 2.5 from the textbook. So basically, we are taking a mole of gas that is an ideal gas and reacting on it in a reversible fashion. We have the initial state, temperature and pressure, and we're adding heat, and in the process of adding heat, work is done. And from this, we're supposed to determine the final state, the change in the energy and enthalpy, and then the heat capacities for nitrogen. Zoom out. So our initial state here is T1 is equal to 273 K. P1 is equal to 1 atm. N1 is equal to 1 mole. And V1 is equal to nRT over P1 is equal to 8.2 times 10 to the minus 2 times 273 K over 1 is equal to 22.4 liters. And it says that this is a constant pressure expansion in which 3,000 joules of heat are added, and the work being done is equal to 832 joules. Constant pressure means that we can write P2 equals 1 atm, N2 equals 1 mole still. We don't have enough immediately to write the volume or the temperature, but we have the work, and we know that work is equal to P delta V is equal to 1 times V2 minus 22.4 liters times 101 joule per atml is equal to 832 joule, which lets us solve for V2, and that comes out to be 30.6 liters. Then that lets us use the gas law to write PV over NR is equal to 30.6 divided by 8.2 times 10 to the minus 2 is equal to 373 K. Okay, so we've got the final state. This is a constant pressure, and we know that QP is equal to delta H, so we immediately know the enthalpy, or the change in the enthalpy, is 3000 joule, and then we use delta U is equal to Q minus W is equal to 3000 minus 832 delta U is equal to 2168 joule. Okay, and next we need the heat capacities. We've got Cp is equal to NCP delta T is equal to delta H. So the constant pressure molar heat capacity is equal to delta H over N delta T is equal to 3000 divided by 100. The constant pressure molar heat capacity is equal to 30 joule per mole K. And then CV, for an ideal gas, CV is equal to Cp minus R is equal to 30 minus 8.314. CV is equal to 21.7 joule per mole K. All right, let's look at problem 2.8 from Gaskell. This is ideal. The version 3 of the textbook has that typo. So in this problem, we've got 2 mole of gas, and we're given the initial state, and we're told that the system traces out a curve given by this equation, and we're supposed to calculate the amount of work done and then the minimum and maximum temperatures during this. This problem I like because it does, you can solve it exactly if you want to, or you can solve it using MATLAB or Mathematica or some other solving software which will significantly improve your life, but you can do it by hand. And I just want to step through how this problem is addressed. So you have your initial condition, P1 equals 10 atm, V1 equals 5 liters, N1 equals 2 mole, T1 is equal to PV over NR is equal to 10 times 5 over 2 times 8.2 times 10 to the minus 2 is equal to 305 K. This equation is a parametric equation, and you may remember this from your multivariable calculus class, but this corresponds to, in the P space, a circle that is centered on 10 atm and 10 liters, and it has a radius of 5. So that corresponds to 15 TM, 5, 15. That out a little more. And what we're doing is we're starting at 10 and 5, and we're tracing out this path, going around and coming back. But in our parameter space, anytime you have a work pair, for example, pressure volume, the area of a closed loop is equal to the work for a cycle. So in our case, the work is equal to pi 5 squared times 101 joule per ATML. So the work is equal to 7,932 joule. And then the next question in the problem is, can you find the maximum and the minimum temperatures during that cycle? And we can. To do this, we start with, just switch pages here. We start with PV equals N RT. So we have T is equal to PV over NR. And then we want to substitute in for either V or for P, and if we take our parametric equation, we can get V is equal to 10 plus or minus square root of minus 75 plus 20 P minus P squared. So clearly this is going to become a little bit messy, and I'm going to refer to this as V plus or minus to correspond to the plus and minus in the equation. Plus minus, plus minus. And now we want to find the maximum temperature, having substituted in V plus and minus. And the way to do that is to take the derivative, set it equal to 0, and find P. And you can do that. It is a little messy. It's not impossible. But I solved it using Mathematica and basically found dp of P V plus minus over NR equals 0. And I wound up with two pressures. P plus, which is 13.54 atm, and P minus, which is 6.46 atm. If I take these values and I substitute them back in, I get T plus is equal to 1117 K, and T minus is equal to 255 K. So that's the approach to solving this problem without the detailed math, but that's just derivatives, which is a review of first semester calculus. Let's now work on problem 3.4 from Gaskell. I kind of like this part of the book. We're finally coming to the point where we're looking at materials and looking at solids. So the problem is to calculate the change in the enthalpy and the entropy when 1 mole of compound, this is silicon carbide, is heated from 25 degrees Celsius to 1000 degrees Celsius, and we're given the constant pressure molar heat capacity as a function of temperature. And this is nice because this is kind of the beginning of materials. Most of the solids we're dealing with are treated at a constant pressure, and we can think about things in terms of relatively simple integrals. I'm going to zoom out a little bit. In particular, we've got the change in the enthalpy to integral from 25 plus 273 to 1000 plus 273 to do everything in Kelvin times N Cp dt. For now, Cp is a function of temperature, so we're going to substitute this equation in, and delta S is equal to the integral from 25 to 273, 25 plus 273 to 1000 plus 273 N Cp T dt. And that's it. This equation is the functional form of heat capacity as a function of temperature in most materials. In most materials, it looks something similar to this. And it starts out down here, comes up, and then it's forward. So let's just write out the integral, why don't we? The integral from T1 to T2 of something with a functional form, a plus b t plus c t to the minus 2 plus d t to the minus 3 dt is equal to a t plus 1/2 b t squared minus, that's because we got a negative in the exponent there, minus c to the t raised to the negative 1 minus 1/2 d t to the minus 2 evaluated at t equals t1, t equals t2. So we can simply substitute in our coefficients and get the answer for the enthalpy. And for the entropy term, the integral from T1 to T2 of A over T plus B plus C to the CT to the minus 3 minus 3 plus dt to the minus 4 dt is equal to a natural log t plus b t minus 1/2 ct to the minus 2 minus 1/3 dt to the minus 3 evaluated at t equals t1, t equals t2. So it's just a matter of substitution, and I would encourage you, those of you that plan to go on and work in this field, which many of you will, to find a mathematical solver to do this for you. MATLAB's now available for free. You can download an open source version of MATLAB called Octave, and there's several Python implementations that are also useful. So basically, you can do a little bit of solving, substitute in, and what you get is delta H is equal to 42.7 kilojoule, and delta S is equal to 59.7 joule per K, joule per Kelvin. Okay, let's look at problem 3.5 from Gaskell. Another problem I enjoy because I think it has a nice materials flavor to it. So basically we're looking at the equilibration of materials at different temperatures. So we have 1 mole of copper that is at 0 degrees C, and we put that in contact with 1 mole of copper at 100 degrees C, and we say that these are going to be joined and isolated so they can't absorb or emit any heat to their surroundings, and we're just looking at how the effect of thermal transport across these. So our systems look basically like this. The hot side is T equals 373 K, and the cool side is T equals 273 K. So when we put these together, heat flows from the hot to the cool side. And if we write out this, and I suppose I should write this here, Q from cool to hot side, we can write these out in terms of the heat capacities. And we're given the heat capacity for copper. So let's do that. QHC is equal to 373, so that's going from the hot side to the cool side, to T star, so that's the equilibrium temperature, N Cp dt, and then flowing from the cool to the hot side, we have integral 273 to T star. These two T stars have to be the same because they're reaching equilibrium, N Cp dt. And because energy has to be conserved and no work is being done, we have negative QHC is equal to QCH. And if we set these two equally to each other, we can solve for T star. Again, I would encourage you to look for a mathematical solver like Mathematica. The student edition of Mathematica costs like $200, and if you get it now while you're just entering grad school, you will use it all through grad school and possibly beyond. So solving for T star, we get T star is equal to 323.318 K, which is 50.318 degrees C. So it's not exactly 50-50, right? We didn't take just 100 degrees and 0 degrees and average them out to be 50. It's a little bit hotter than that. And that's because there is entropy. There's an irreversible entropic contribution. And why do we know that it's irreversible? We know it's irreversible because it's a spontaneous process. So many of the problems that we worked on, we say, well, you know, we got a system, it's in equilibrium, we can move it in a reversible fashion. And in doing so, we're saying that, you know, everywhere along the path, it's in equilibrium. And here we start out with something which is explicitly not in equilibrium, and we're watching it equilibrate, which makes it both spontaneous and irreversible. So there's going to be an irreversible change in the entropy, and we can write out the entropy for the flow of hot to cool and cool to hot. So we get delta S HC is equal to the integral from 373 to T star, and I'll just substitute in for that. N Cp T dt and delta S CH is the integral from 273, because it's the cool side, to T star, again substituting in T star, N Cp T dt. And when we do that, again substituting in our values for the heat capacity and the equilibrium temperature, we get delta S HC is equal to minus 3.5482 joule per Kelvin, and delta SCH is equal to 4.1459 joule per Kelvin. So the net change in the entropy for this system is delta S HC plus delta SCH. Delta S is equal to 0.5977 joule per K. And that change in entropy is why we have a equilibrium temperature which is slightly above the average of the two. So let's now look at the final problem in Chapter 3. This is problem 3.6. And this is a problem about a reversible heat engine, but the reservoirs which it is taking heat from are finite size. So basically we have some hot reservoir with heat capacity C2 and a cool reservoir at temperature T1 with heat capacity T1, and a system. Heat goes in, 2, heat goes out, and in the process work is done. And this is a system, let me zoom out, this is a system such that as heat flows from the reservoir into the system and then out, the temperature of the hot reservoir gets cooler and the temperature of the cool reservoir gets hotter until they reach equilibrium. So there's going to be some equilibrium temperature, and the question is how much work can come from this, and we're looking at the maximum work possible for a system with because it's completely reversible. So there's no there's no entropic degraded mechanical energy. And because this is a reversible system, we can take this all as though, you know, the heat all gets transferred in kind of one lump sum. We don't have to think about it on a cycle by cycle basis because there's no entropic change. So let's say that in one fell swoop all of the heat necessary to go to the equilibrium temperature gets transferred and then gets transferred in. So that means that we can write out that heat Q2 is equal to heat capacity. So this is the heat leaving the system, heat capacity of system 2, and that's T2 minus T, I'm calling TF, the final heat, right? And that's greater than 0 because T2 is larger than TF. And then the heat that gets transferred in, Q1 is equal to C1, and that's going to be TF minus T1. And again, that's greater than 0. And I changed the signs here in order for us to just talk about the magnitude of the heat. Because if we know the magnitude of the thermal energy that goes in and the thermal energy that goes out, then the work is simply Q2 minus Q1. So we have these. The next question is, how do we get what this final equilibrium temperature is? And we can get that by recognizing that it's a reversible engine. Therefore, we can use the constraint that the total change in the entropy has to be equal to 0. So delta S tot, and this is the entropy change at the here where heat flows in. That's going to be T2 TF C2 over T dt. That's the change in the second thermal reservoir. And then T1 to TF C1 over T dt. That's the change in the first thermal reservoir. Those two together have to be equal to 0. And I cannot stress enough how nice it is to have software that will solve math for you, so you don't have to write all of these out and go through 2 pages of algebra. And if you do that, then you wind up finding TF is equal to exp of C1 natural log T1 plus C2 natural log T2 divided by C1 plus C2. So this is the equilibrium temperature. And then simply taking this and substituting it into Q and into W, we get W is equal to C1 T1 plus C2 T2 minus C1 plus C2 times T1 raised to the C1 over C1 plus C2 times temperature 2 raised to the C2 divided by C1 plus C2. And that's the work that's done in this reversible engine. Again, the algebra is a bear, so look for a way to engineer a solution for yourself.